Good morning to all. Let us start the wave optics. Today, in this lecture, I am going to cover the definition of wavefront, Huygens principle, reflection of light based on Huygens principle, refraction of light based on Huygens principle, behavior of wavefront in a mirror, lens and prism. So let us understand or revise the electromagnetic wave before starting the wavefront. Now, electromagnetic wave. Now, as you know that electromagnetic wave is the propagation of the magnetic field and the electric field vector in a direction perpendicular to the mutually perpendicular to both. So, since variation in both electric and magnetic fields occur simultaneously, therefore they attain their maxima and minima at the same place and at the same time. The direction of electric and magnetic fields are mutually perpendicular to each other and as well as to the direction of the propagation of wave. The speed of electromagnetic wave depends entirely on the electric and magnetic properties of the medium in which the wave travels and not on the amplitude of their variations. Wave is propagating along x-axis with the speed c is equal to 1 upon under root mu naught epsilon naught. For discussion of optical property of electromagnetic wave, more significance is given to electric field vector. Therefore, electric field is called light vector. Now let us discuss wavefront. Wavelet is the point of disturbance due to propagation of light, and wavefront is the locus of points or the wavelets having the same phase of oscillations. Line perpendicular to a wavefront is called a ray. This is a wavelet. It is the point of disturbance. Now from this point of disturbance, the light is spreading in all the directions. So wavefront is the locus of points having the same phase of oscillations. From this figure, we can say that these circles, all the points on these circles are in the same phase. So this circular or the circle is a wavefront, and a line perpendicular to the wavefront is called. So red line is a ray and the purple circles are the wavefront. So we can say if the point source is there, then the spherical wavefronts are produced, because from a point source the light travels in all the directions and the locus of all the points having the same phase is of the shape spherical shape. So we can say that a spherical wavefront is produced with the help of a point source. Now let us see or the shape of the wavefront for a cylindrical source. Now this is a cylindrical source. From this cylindrical source, the light is traveling in all the directions. So the locus of all the points having the same phase is of the shape of cylinder. So we can say from the cylindrical source or the linear source, the cylindrical wavefront is obtained. Instead of cylindrical source, I must use the word linear source. So from a linear source, cylindrical wavefront is produced. And from plane wavefront, how the plane wavefront is obtained? Because when a source is very far away, whether it is a point source or a linear source, when the source is very far away, then the ray of light will become parallel to each other, and in that case the locus of all the points will be of the shape of a plane, just like as shown in the figure. So blue envelope is the wavefront, pink dots, they are the source or the wavelets, and the red line is shown by the ray. So in this way we can say that a point source produces spherical wavefront, linear source produces cylindrical wavefront, and when the source is very far away, then at very far points the plane wavefront is produced. Now, Huygens construction or Huygens principle of secondary wavelets. Now, S is the point source. From this point source, the rays are moving in all directions. Now, in all directions, so these dots, they are the points on the same these points having the same locus. If the locus of the points having the same face is connected, then the spherical wavefront is shown. So blue color is the spherical wavefront. Now, according to the Huygens, that each and every point on the wavefront will behave as a fresh source. So from this source, from all these points, the secondary wavelets or the secondary wavefront will start moving, or this all the points on this secondary wavefront or in this wavefront will behave as a fresh source from where the ray will start and move in all the directions. Now, if we find the locus of the points having the same phase, then see this blue light is shown is the locus of the points having the same phase. So this is a new wavefront, and which is again in the shape of a spherical wavefront is produced. Now, at a very far away point, dot line shows that the point is very far away. So these dots, they are again the points on the secondary wavefront, and these points will behave as a fresh source of light, and from here the light will again move in all the directions. So in this case, the locus of the points having the same phase will be of the shape the plane wavefront. So here the new wavefront will be of the shape plane. So here the wavelets or the fresh source is shown by the dots, red dots on the wavefront. Each point on a wavefront acts as a fresh source of disturbance of light. The new wavefront at any time later is obtained by taking the forward envelope of all the secondary wavelets at that time. So these 2 points are the points given by the Huygens principle. So Huygens principle, that is, each point of a wavefront act as a fresh source of disturbance of light, and the new wavefront at any time later is obtained by taking the forward envelope of all the secondary wavelets at that time. Now the question arises, why only the forward envelope? Why not the backward wavefront? Backward wavefront is rejected. Why? Amplitude of the secondary wavelet is proportional to half 1 plus cos theta. This is the formula for the amplitude of the secondary wavelet. Means amplitude is proportional to this. Now, for the backward wavefront, theta will be equal to 180 degree and cos 180 is minus 1. So 1 plus cos theta is equal to 0. So the amplitude for the secondary wavelet in the backward direction is 0. So we will not obtain the backward wavefront. Now let us explain the laws of reflection at a plane surface on the basis of the Huygens principle. Now this is any plane surface xy. The wavelets or the rays are coming or falling on the surface xy and reflecting. So AB will be the incident wavefront and CD will be a reflected wavefront. How we obtain the reflected wavefront? That is, the ray of light from point B reaches to the point C. So the time taken by the ray to reach from B to C will be same as, in this time the A will reach to point D. So the time in which B reaches to C, A will reach to D, and taking the arc on this reflected ray, then CD gives us the reflected wavefront. Now AN is the perpendicular. Now let us see that this is the angle I, angle of incidence. So angle of incidence, that is again equal to this side, angle of reflection, and ACD will be equal to same angle of reflection R. Now EF and G, they are the another points on the incident wavefront and the reflected wavefront. So AB incident wavefront, CD reflected wavefront, and XY is the reflecting surface. Let C be the speed of light, and let T be the time taken by the light to go from B to C, or from A to D, or from E to G through F. So time will remain same when time taken by all the points on the incident wavefront AB to reach to any point on the reflected wavefront CD will be same. B means the time taken by the ray from B to C means when B reaches to C at the time, since A is incidenting on the surface earlier, so by the time B reaches to C, A will reach to D. Similarly, the point E, the ray at point E will reach to F and reflect back to point G. So we can say that T is the time taken by the light to go from B to C, from A to D, or from E to G through F. Then we can say that time is equal to distance upon velocity. So time is equal to EF upon C plus FG upon C. Now EF from the triangle AEF, look carefully, from the triangle AEF we can write AEF is equal to AF sin I, and in triangle FCG, FG can be written as FC sin R. I think this is a mathematics you can understand very easily. Now since FG is equal to FC sin C, now look at here, FC can be replaced as AC minus AF. Now in place of FC write AC minus AF, rearrange the term, we will get AC sin R plus AF in bracket sin I minus sin R. So here in place of AFC we have written AC minus AF, then rearranges the terms and we get this expression, that is AC sin R plus AF sin I minus sin R upon C. Now for rays of light from different parts on the incident wavefront, the values of AF are different. But light from different points of the incident wavefront should take the same time to reach the corresponding points on the reflected wavefront. Now listen again, that for rays of light from different parts on the incident wavefront, the values of AF are different. But light from different points of the incident wavefront should take the same time to reach the corresponding points on the reflected wavefront. So it means we can say that T should not depend upon AF because AF is changing. So this is only possible when this term is equal to 0. Since AF cannot be equal to 0, so we can say sin I minus sin R is equal to 0, or sin I is equal to sin R, or I is equal to R, which is the laws of reflection. According to law of reflection, Snell's law of reflection, that angle of incidence is equal to angle of reflection. So now here we have proved the laws of reflection on the basis of the Huygens principle. Now we will try to solve or to prove the laws of refraction at a plane surface using Huygens principle. So let us, XY is a refracting surface separating the two medium. Other one is a rear in which the velocity of speed of the light is c and the refractive index is mu1. The second medium is the denser medium where the speed of light is v and the refractive index of the medium is mu2. Now these rays are falling on the surface xy. Now since these rays will refract or the bend towards the normal as the second medium is the denser medium. So if AB is the incident wavefront, then to obtain the refracted wavefront, we will make a arc on this AD equal to VT and join the C and D. So CD is the refractive refracted wavefront. Now drop the perpendiculars, then angle I is equal to angle BAC, that is again angle of incidence. R is the angle of refraction, which will be equal to angle ACD. So AB incident wavefront, CD refracted wavefront, XY refracting surface. So if C be the light, speed of light, T be the time taken by the light to go from B to C, or from A to D, or E to G through F. The principle is same, that they will take the same time in reaching from B to C, or from A to D, or from E to G. So again T is equal to EF upon C plus FG upon V. Now here just see, T is equal to EF upon C, because EF is in the medium in which the speed of light is V, and FG is the distance in the medium where speed of light is V. So here the difference is T is equal to EF upon C plus FG upon V. Again, in place of EF we can write AF sin I, and in place of FG we can write FC sin R. Again, FC can be divided into two parts, that is FC again is equal to AC minus AF. So in place of FC writing these AC minus AF, then rearranging the terms, we will get this expression. The T is equal to AC sin I upon V plus AF sin I upon C minus sin I upon V. Again, for the same reason, for rays of light from different parts on the incident wavefront, the values of AF are different, but light from different points of the incident wavefront should take the same time to reach the corresponding points on the refracted wavefront. So we can say that T should not depend upon AF, and this is possible only if sin I upon C minus sin R upon V is equal to 0, or we can say that sin I upon C is equal to sin R upon V, or we can say that sin I upon sin R is equal to C upon V, and we know that C upon V is equal to mu, so we can say that mu is equal to sin I upon sin R, which is the Snell's law of refraction. So using the Huygens principles, we have also proved the laws of refraction. Now let us discuss the behavior of plane wavefront in concave mirror, convex lens, concave lens, and prism. Now this is a concave mirror. Now plane wavefront. Plane wavefront means the rays are parallel to the principal axis. They are falling on the concave mirror. After refraction, they reflect and meet at a point which is the focus of a concave mirror. So see that AB is the plane wavefront and CD is the reflected wavefront. The shape of the reflected wavefront is the converging. So we can say that plane wavefront after falling on a concave mirror changes to converging spherical wavefront. Similarly, for convex mirror, the rays after reflection they diverge, so the plane wavefront changes into the diverging spherical wavefront. For convex lens, so plane wavefront changes to converging spherical wavefront, and for concave lens the plane wavefront changes into diverging spherical wavefront. So the whether it is mirror or lens, depending upon the nature, if the nature of the mirror or the lens is converging, then plane wavefront will change into the converging spherical wavefront, and if the nature of the lens or mirror is diverging, then the plane wavefront changes to the diverging spherical wavefront. So AB is incident wavefront and CD is the reflected or refracted wavefront. Now for a prism. In case of a prism, the plane wavefront remains the plane wavefront, only the direction changes. So let us see that blue one is the plane wavefront, incident wavefront. After passing through the prism, it is again the plane wavefront, only the direction is changed. So that is all for today's lecture. Thank you and have a nice day.